this just in case.
Awesome. Thank you.
Then their temperature changes to some, let's say 25 degrees Celsius, for example, like that, okay? Now what happens next is, what we can do is, let's say you have like 1 mole per liter of this and 1 mole per liter of that. That's the concentration. Do you know much about concentration at all?
Not in a depth, but I do know the general idea of, yeah.
So the general idea is, you know, concentration is equal to number of moles divided by volume. So if you have in a small space, you have a little bit of a, like that. Okay, and that is going to combine with, so that's volume, this much volume with this much moles in there. So we can say that if that balloon is 1 liter, and each dot represents, let's say, 1 mole, 1, 2, 3, 4, 5, 6, 7. So you can say that this is 7 mole in a liter. Is that right?
Yes.
So 1, 2, 3, 4, 5, 6, 7. Yeah. So if I also have a much bigger balloon, let's say that's 4 liter, and let's say I have the same number of moles. 1, 2, 3, 4, 5, 6, 7. Okay. Now, what is the concentration here? Is it going to be lower or higher?
It's going to be lower.
It's going to be lower, that's right. So the concentration for this one is 7 moles divided by 4 liter. In this case, the concentration is 7 mole in 1 liter. That's why you get 7 mole per liter. In this case, it'll be about 1.7 something, okay? 1.7 mole per liter, okay?
Yeah, 1.75, yeah.
1.75, that's right. So yeah, that's less concentration, higher concentration, but they contain the same amount of moles, okay?
Right.
So that's a little bit of idea behind concentration. And this is a little bit of idea behind what's known as exothermic reaction, okay? So exothermic reaction is a reaction that releases heat and makes the water warmer. And we say that the change in enthalpy is negative.
Okay.
So this is known as change in enthalpy. Okay, so that's a little background there. So this reaction here is given by delta H. If you look up the heat of neutralization between, so heat of neutralization of NaOH and HCl, it says that it's about that much, negative 57.9. Hold on, one source enthalpy change neutralization gives a value of that for sodium hydroxide solution being neutralized. So yeah, it's that value, okay? So it's about that much, which means 1 mole of this and 1 mole of that combined to give that, but the amount of heat that will be generated will be 57.9 kilojoules.
Right.
So you do physics as well, right?
Yes.
So you understand the concept of joules, I guess.
Yeah.
So yeah, so what that means is that this is per mole, So 1 mole gives that much energy. Okay.
Right.
Now, so if you have, let's suppose that you have 1 mole. Don't worry about the concentration there. Okay. Let's say you have 1 mole of this and 1 mole of that. Okay. How much heat will be generated?
Oh, just.
Would that be that times by 2 because there are 2 moles, or would it be just that much?
Well, if there's 2 moles, should it be times by 2?
Okay, so it is when it says per mole, it's actually just 1 mole of this guy. Okay.
Right. Okay.
Or 1 mole of this guy. So it's not going to change. So if this is 1 mole, the energy that's generated will be negative 57.9 kilojoules.
Okay.
Okay. so in this case, it's just per mole, per 1 mole of either of those, not both of them. Okay.
Oh, either. Okay, cool.
Yeah. So if you have 2 mole, however, and 2 mole here, and 1 mole generates that much energy, right? So in this case, because it's 2 mole, 2 mole, it'll be negative 57.9 times by 2. So it'll be about 116 kilojoules. Okay.
Okay.
Yeah.
Oh,
Does that
right.
does
Okay,
that does that make
Yep.
sense?
Oh,
Now,
no, yeah, that makes sense.
if I have 2 mole and 1 mole, however, what would it be then?
Oh.
So if it is 1 mole plus 1 mole, it'll give off 57.9 kilojoules. If it's 2 mole, 2 mole, then it'll be negative 115.8 kilojoules. Twice this one, okay?
Right.
Well, what about this one then?
Is it just 115 minus 57?
The answer is just 57.9 kilojoules.
Oh, okay.
So let me give you an analogy for that, okay? So let's say this is acid, okay? Let's say 1 acid plus 1 base will give you this much energy. That's 57.9 kilojoules, right? Now, if I have 2 of this and then 2 of that, they will neutralize and give me 2 of those, right? 2 of bam, bam, like that, okay? So that'll be 115.8 kilojoules, true?
Right.
Now, if I have 2 of this and just 1 of that, then what's going to happen is this is not going to do anything. It's just a reaction between this, and this one has no one to react with, and this will be exactly the same as this case over here.
Oh, okay, yeah.
Does that make sense to you?
Yeah.
So this is equal to 57.9 kilojoules. Make sense?
Right, yes, okay, yeah.
Yeah, so that's really, really important. Now, having said that, now we're going to move on to a different concept. So another concept is this equation, Q equals to mc delta T. Now, M is known as the mass. Delta T is known as the change in temperature. And the C is known as the specific heat capacity. Or it's just specific, sometimes just known as specific heat, and Q is the amount of heat. All right?
Okay.
So the specific heat of water is about 4,180 joules per gram per Celsius. So what that means is, this is actually kilogram. So what that means is to raise 1 kilogram temperature of 1 kilogram water by 1 degree Celsius, 4,180 joules of energy is required. Okay, so if you have a kilogram water, let's say that's 20 degrees Celsius. In order to raise this one to 21 degrees Celsius, then you need that much energy. That's what is known as the specific heat. Okay?
Right, okay, yep.
Now, if I want to raise this 1 kilogram object from 20 degrees Celsius to 30 degrees Celsius, can you tell me how much energy is required?
10 times full.
10 times that. Right,
yeah.
That's right. So let me give you another question. If you have 7.25 kilogram, and this is currently sitting at 10 degrees Celsius, you want to raise it to about 35 degrees Celsius. Can you tell me what the amount of heat required is? just have to use that formula.
Yeah.
So
And then
it's
that's
7.25 kilogram times by 4,180 joules per kilogram Celsius. So just have to make sure that this matches that one, okay? Kilogram.
Awesome. I got 757,625.
So you do that, then you get the answer, okay?
Yeah.
So let's pull up the calculator.
Oh, right. Sorry, I did something wrong. My bad.
So 454,575.
Yeah, I just added another numeral. Sorry about that.
Yeah, that's all good. So that many joules, okay? This many joules. Sometimes the C is known as 4.18 instead of 4,180. In that case, this will be kilojoules per kilogram degree Celsius.
Right.
So if that is the case, then I'm going to give you another question, okay? Question 2. Let's say you have 1,750 gram of water, okay? Actually, I'm going to give you all three of this. So 4,180 joules per kilogram. So you can also have joules per gram Celsius.
Okay.
So in that case, it'll be 4.18 as well.
Okay.
So if it's a joule per gram, 4.18. If it's kilojoules per kilogram, if these two match, there's no kilo, then it's 4.18. But when it's a kilogram down here, but then you see, when you convert that into joules, that's 4,180 joules, isn't it?
Right.
Over 1 kilogram. So that's how you do it. And 1,750 gram of water. It is at 13 degrees Celsius. It's going to be raised to 100 degrees Celsius. How much energy is required? Then if you want to use gram, then you got to choose this guy, right?
Yeah.
Yeah. So it'll be what, so you have a choice. So if you do that, so whenever you use MC delta T, this equation, it's better to include all the units.
Right.
Because sometimes it's very confusing. Sometimes you may have kilogram here, but then you may, if you have something like, that's gram, but if you have something like, 4,180 joules per kilogram, you see how the gram doesn't cancel out, gram and kilogram?
Right.
So this is wrong, okay?
Right.
So you gotta have a joule per gram, and there's 4.18 there, and the temperature change is 87, isn't it? 87.
Yeah, so I got 636,405.
Yeah. So that's how you do this problem. Now, the whole aim of this exercise is you have acid and you have base. This whole practice is about acid plus base, and that gives you some heat. Of course, it gives you salt and water plus heat, right?
Right.
Now, we put base and acid together, and we observe some temperature change from going from 18 degrees Celsius to, let's say, 22 degrees Celsius. Let's suppose that this is like 50 mil and 50 mil.
Right.
So originally, each one of them were 18 degrees Celsius, but then when you combine them together, it became that. All right.
Right.
So what we can do is then figure out how much heat was generated from this, the mass of the water. So because this is 100 mil is roughly the same as 100 gram for water.
Right.
So there's a direct correspondence between volume and mass for water, okay? So because 1 centimeter cubed, the definition of gram and all this volumetric system is based on water. So 1 centimeter cubed is the same as 1 mil, and that's 1 centimeter by 1 centimeter by 1 centimeter. So inside this 1 centimeter by 1 centimeter by 1 centimeter cube, that's 1 mil. But inside of that, if you trap water in that volume, if you have that much volume of water, it'll weigh 1 gram.
Right.
Make sense?
Mm-hmm.
So if you have 100 gram times by, because that's gram, you do 4.18 joules per gram Celsius, and then times by 4 degrees Celsius.
Yep.
Then you get 100 times by 4.18 times by 4. So that gives you 1,672. Is that right?
Yes.
Is that in joules or kilojoules?
In joules.
In joules, that's right.
Mm-hmm.
Now let's suppose that this many joules came out from. So let's say in this case you have, let's say, 3 mole and 3 mole. Okay.
Mm-hmm.
Then what we can do is Q divided by N. That'll give you the delta H.
Right.
So 1,672 joules divided by 3 mole. Then what you get is that divided by 3. Then you get that much joules per mole, and divide by 1,000. Then you have that many joules per mole, kilojoules per mole.
Right.
So this was a 557 joule per mole, and this will be 0.557 kilojoules per mole. Okay.
I have a question though.
Yep.
So when this task was introduced to us, our teacher said that Q directly equals to delta H.
No, I don't think so.
Okay. All right.
I'll give you the proof for it. Okay.
Okay, sure. Oh, I think she said that because we are only using 1 mole per liter solution. Does that make any change to it?
If it does, yes. If it's just one, yeah, that's right.
Okay. Okay.
Have a look at this. So generally the Q is N delta H, so delta H is Q over N.
Mm-hmm.
Okay.
Yeah. Awesome.
Yeah. So
yeah, I just wanted to double check just to make sure that my teacher was wrong.
Yeah. Okay, that's fine. So let's move on to this experiment.
Mm-hmm.
What your teacher has done here.
Yeah.
All right. Now, first of all, there's a problem with this method here because you have 50 ml of 1 mole per liter NaOH was added to 50 ml beaker. Mm-hmm. That means inside of the maximum capacity is 50 ml, right?
Oh, right. And they filled it up to 50 ml.
And then you filled it up with 50 ml of base.
Right.
But then if that's the case, you can't add any more acid to it, right?
Exactly, yeah.
So I would change that to 100 ml, okay? So, or more, so that's a 200 ml. Mm-hmm. So this is what I did. If you look at what I wrote here, okay? Yeah. So your teacher said, just gonna actually copy and paste all of that.
Can you share this document with me later?
Yeah, I'll do it. Yep.
Awesome, thank you so much.
So what I did was, so change to a 200 ml beaker, and it says initial temperature measured using a digital thermometer and a recorder, right? But I said it was added to about 200 ml styrofoam foam beaker, and the initial temperature of the solution was measured using a digital thermometer and was recorded. The thermometer was not removed. I added this bit because otherwise some of the NaOH molecules will be lost. Right? If you stick thermometer in and then you remove it, then some of the NaOH will be gone, right? So we don't want that to happen. The beaker was then covered with aluminum foil. Some different, any kind of foil is fine because we want to contain as much heat as possible. We don't want any heat to be removed. So in order to contain,
class was using styrofoam lids. Should I?
Maybe styrofoam. Well? Yeah, styrofoam lid. in order to contain any heat that might be generated, the lid was prepared in a way that facilitates easy access to pour in acid and easy to cover back again. So you can just change the grammar there. I just wrote some, it's just something that just came to my mind. So you can just fix the grammar later. So what I mean by that is you just prepare a styrofoam cup in order to keep the heat in, and you prepare a lid, and you have this thermometer that's stuck in, and you also have your stirring rod. Okay? That enables this thing to be stirred. Okay?
Yep.
That's the bit added. So prepare 100 ml solution of acid. Just prepare it. So what you do is you fill it up with the base first, so that's base. And then you have you prepare 100 ml of acid somewhere, and then you put the lid off partially. So if the lid is sort of like this, then you inject acid in there. Okay.
Okay. Yeah.
Remove the lid of the beaker and pour in 10 ml of the prepared acid solution into the beaker, and close the lid immediately. Stir for a few minutes. Maybe you can say stir for about 30 seconds. I think that'll be enough. And wait until the temperature rises to a certain level without increasing any further. So you want to wait until the temperature settles.
Right.
Okay, and record the temperature. Okay. So what that means is, if you have a 50 ml here, so they're the same concentration. So if you have the 1 molarity, and this is also 1 molarity, and if you add 10 ml into it, so you add 10 ml there, that will neutralize 10 ml, right? So 1/5 of the base, right? So that'll be neutralized. So when that happens, then of course what's happening is, if you have a base like 1, 2, 3, 4, 5, and then you have 1, 2, 3, 4, 5. So let's say you have a 50 ml here, okay? And then you add 10 ml. Then the amount of heat that's generated will be based on this and this, right?
Yeah.
So you get this much heat being generated.
Right.
And that'll result in some change in temperature, right? And then you add another 10 ml, and this will neutralize that one, right? And then you get another amount of heat generated. So this will result in some change in temperature.
Right. Yeah.
So let's say you started with the 18 degrees Celsius. After this one, you could get maybe 19 degrees Celsius. So the change in temperature is about 1. So you get up to 19 degrees Celsius. And then you add this one, they neutralize, and then the temperature change will be 1 as well, because you get the same amount of, it's expected to have less and less effect. Because, temperature change will be less and less. The amount of energy produced is the same, but you have to heat up more water, right?
Right.
There's more water coming in. So with the same amount of energy, the temperature change will be a bit lower, But anyway, temperature will keep on increasing, right? Temperature will keep on increasing.
So sorry, if I change the measurements of acid, which the method that the teachers have given does, that I believe, so the temperature would increase or decrease as I add more acid?
Well, it'll of course increase, because it's an exothermic reaction,
right? And
it'll release heat. So as you can see in your teacher's report, the temperature increases, right, as you add more acid to it. So it is expected to rise because heat is being generated. Okay.
And should I talk about this only 1 mole reactors, only 1 mole in my in my report? Should I talk about it in my investigation? part of it? Or
that I'm not really sure.
okay.
We'll talk about that later, okay?
Okay, yeah, sure.
Yeah, we'll talk about that later. We just need to get this concept through.
Right.
Anyway, so what I did was, so your teacher said the required volume of 1 mole per liter HCl as per data table was added to the beaker. The reaction was stirred twice and final temperature was recorded. So your teacher got some results looking like this one here. Is it this one? Yeah, that's right. So he added 0 mil, and then you see there's no change in temperature pretty much, right?
Yeah.
So you have a 50 mil of NaOH.
Mm-hmm.
You add 20 mil, temperature changes from that to that.
Right.
40 mil, temperature changes from that to that.
Mm-hmm.
Well, if you add 60 mil,
Mm-hmm.
the temperature must have risen a bit higher, right? Well, so why is it 19.1? So that doesn't make any sense, right?
Right.
Yeah.
Mm-hmm.
So I think that's an outlier.
Mm-hmm.
So here also, it's a bit weird. So no change in temperature pretty much. A little bit change a lot,
Mm-hmm.
and then change less. So that must be an outlier.
Yeah. I think
that's also
I think
a
they
mistake.
purposely done that because they in the original document they said that they changed like the type of thermometer. They went from a digital to an analog. So I think they've done that just to have something to write about for the students. I think
Right. Okay.
Yeah, that could be the case of that.
So that makes sense. Okay, that's fine.
Mm-hmm.
So this is something that's wrong, and I think that's something wrong as well.
Yeah. And
also, you see how they added 20 mil, 40 mil, and the 60 mil?
Mm-hmm.
But adding 60 mil is no different from adding 50 mil. Right. The amount of heat that's generated is still the same, right?
Right. Yep.
Actually, this could not be an outlier actually, because if you add more water,
mm-hmm.
then there's more water to heat up, right?
Mm-hmm.
So when you add more acid, what's going to happen is you're generating more heat for sure. So temperature will increase more, right?
Yeah.
So that's what you can see over here and over here.
Mm-hmm.
But there's also another effect, which is because you're at the same time, you're generating more heat, but at the same time, you have more water. So in this case, you have to heat up 90 mil of water compared to 70 mil of water.
Right.
So that has sort of negative effect on this one. So it causes the water temperature to rise not as high.
Right.
Does that sort of make sense?
Yes.
So in this case, in the last case, you added, so the amount of heat that's generated is the same as when you add 50 mil here. But then you are having unnecessarily larger volume of water. That's why this might be leading to this much temperature rise.
Because there's so much
there's so much water, volume of water to heat. So that's why the temperature rise is not as much, but I still think it has to be higher than that.
Okay. Yeah.
So we can think about that later. Okay.
Yeah.
Yeah.
Definitely.
So anyway, this is I think what would have been a better method.
Mm-hmm.
All right. So let me tell you the difference between my method and your teacher's method. Okay.
Okay.
It looks like, so we have, in our situation, we have a beaker and we have some base onto it. And then usually this would be a better solution. You add 10 mil.
Mm-hmm.
So why add 10 mil instead of 20 mil? Because in this case, we saw some disaster happening, because in this case over here, if you do this in increment of 20 mil, you end up with 60 mil, and 60 mil is unnecessarily, that's not going to produce any more heat than adding 50 mil, right?
Right.
Well, do you understand exactly why adding 60 mil is no different from adding 50 mil?
Yeah, because there's only only
Yeah.
like
So
50
we
mils
talked
of,
about this, right? So we have
yeah.
we have like this much acid and then this much base. This will give you, let's say that much energy, you know. Like that, right? That makes sense, right? But having extra acid, that's not going to change the amount of heat that's produced.
Exactly, because it's only 50 to 1.
So I think the better method would be to do this in 10 mil increment. So you add 10 mil, and that neutralizes 10 mil of the base, and then you add another 10 mil of the acid, another 10 mil, another 10 mil, right? So just keep doing that at a record temperature, right?
Yeah.
So that would have given us the result of something like this. This is the acid, and this is the base, NaOH, and this is 0, 10, 20, 30, 40, 50. And the temperature initial, temperature final, this is always 50 mil. And there's no reason to go beyond 50 mil, you know?
Yeah, exactly.
So temperature initial could be 18, and that remains as 18 because there's no acid added, right? And then you start with 18 and you add 10 mil, this temperature could rise to 19. And then you start from 19 and then you add another 10 mil, right? That's the total volume becomes 20. The temperature rises 20, and then 20 and 21, and then 21 to 22, and 22 to 23. That would have been a better, I think.
Oh, okay. So you're talking about having the same styrofoam cup, we're just adding more.
Yeah, just same styrofoam cup and then just adding more acid to it, okay? So this will be this will be more, I would say, so there are some uncertainties associated with this method.
Yeah.
Because you're using the same cup, and this will take longer time to do it, so you are more exposed to heat escaping.
Right. Okay.
Yeah.
Because I wasn't quite sure if the teacher's one they kept in the same styrofoam cup or on a different one. I thought they kept in each tested a different styrofoam cup.
Yeah, so that's what they did. That's why they have the same. It's not like that to that, and then that become. It looks like that became that, right?
Yeah. But
it rose to that, but then that's no longer. That's not the starting point of that one.
Right.
So it appears as though your teacher had prepared a few cups, each having 50 mil of base. And then added 20 mil, 40 mil, 60 mil. Yeah, like this one. So
do you think I should?
So they all pretty much started at 18 degrees Celsius.
Yeah.
That's why they don't. That's why they're not connected like that. Okay.
Yeah. Okay. Do you think I should? Do you think I should use your method or their method?
I don't know. So if you were to do your own experiment, so I'm not even sure what this whole online prac is about. You know. So I'm still discovering it. it. I think one thing you have to do.
It's kind of the same.
Yeah. Still clueless. But I think first task I think is to at least analyze your teacher's method and so just analyze every single aspect of this prac over here. Okay.
Okay. Awesome.
Yeah.
Yeah.
But this is method 2. This will give us completely different result. Okay.
Yeah.
So I'm not sure. So this is an online thing. So can we just generate data? So I'm not sure about that.
I'll have.
But based on this stuff, I'm just gonna take that for granted. I actually changed a little bit. That one there. So I found something wrong with that one, and so there are a lot of information missing. It has to be 50 mil. I know it was added to 200 mil beaker, and the initial temperature measured using the thermometer. So you have to say prepare 4 beakers. Prepare for 50 mil of this much in 200 ml beakers, okay?
Mm-hmm.
In 4, okay, so something like that. It has to be something like that. And initial temperature, and measure the initial temperature of each beaker, right? Using a digital thermometer, right?
Yeah.
It has to be something like that. Beaker was left open to allow easy addition, so step 2. And then what's just in 3 steps, right?
Mm-hmm.
To the first beaker, to the second beaker, add a 20 ml of acid. To the third beaker, add 40 ml. To the last beaker, add a 60 ml beaker, right?
Right.
Yeah, 1 mole per liter HCl as per data table. Yeah, blah blah blah. The reaction stirs twice and final temperature was recorded. For each volume of acid, so step 1, 2 is repeated until 3 trials have been completed. So this must have been the better method,
Mm-hmm.
which truly reflects what was done here, right?
Mm-hmm.
Now, but if I were to do this more accurately, I would follow this method. So this means pretty much what I explained over here. So you just prepare 1 beaker, 50 ml,
Mm-hmm.
add 10 ml, measure temperature, add 20 ml, add another 10 ml, so that which makes it, you're not adding 10 ml and 20 ml and then 30 ml.
Mm-hmm.
You're adding 10 ml and then 10 ml and then 10 ml and then 10 ml, etc. Okay?
Right. Mm-hmm.
So total volume becomes 10 ml, 20 ml, 30 ml, 40 ml, 50 ml.
Mm-hmm.
And then you just do it like that. And this would have been, I think, better result. I'm just saying it would have been better. But let's just park this method here as it is. So
Mm-hmm.
you can use that if it's necessary next time.
Oh, yeah, sure.
Sources of error, of course, heat could escape. Even with lid on and styrofoam, heat escape still occurs. And after pouring some acid, we wait a few minutes for temperature to settle. So during this process, heat may escape also.
Mm-hmm.
With the teacher's method, when 60 ml is added, and if we assume more reaction will occur beyond 50 ml, we may arrive at inaccurate results.
Right.
See? So if we base our number of moles based on, if we base our number of moles on this volume, then of course we will get wrong result, right?
Right.
Yeah, and so I'm gonna just skip this bit for now.
Okay, yeah, sure.
I'm not gonna look at the third 24, so still the same thing, but temperature, so there's nothing there, that's negligible. So that goes up, that goes up, that goes up. What does it say here? The final temperature in the third trial was recorded using an alcohol thermometer as the battery went out flat on digital thermometer. Okay, we did not check the temperature in these experiments using alcohol thermometer before adding.
Mm-hmm.
What does it mean by we did not check the temperature of these experiments using the alcohol thermometer before adding the acid? So this is the temperature after adding the acid, right?
Yes.
This is the temperature before adding the acid. Mm-hmm.
Mm-hmm. Yeah.
So what this is saying is that this wasn't measured.
Oh,
right?
they just assumed that it's.
Where did they get these numbers? That's number one mystery, you know?
Yeah. So they must have assumed.
Also, another source of error you can consider is, the initial temperature of the NaOH was taken as the initial temperature of the HCl as well. Teacher did not measure the initial temperature of the HCl. And usually, both temperatures must be measured, and since they are of the same, must be measured, and take the weighted average of them, okay?
Mm-hmm.
For example, if you have NaOH as is 50 mil and is at 18 degrees Celsius,
Mm-hmm.
18 degrees Celsius, and the HCl is, let's say, initially 18 point, let's say 4 degrees Celsius is, let's say, 10 mil of HCl is added to it, and is 18.4 degrees Celsius.
Mm-hmm.
Then the initial temperature must be taken as, this is a 5:1, so must be 18 times by 5 plus 18.4 times by 1, and divide this whole thing by 6.
Why 6?
Because it's 50 mil, 10 mil, so total is 60 mil, right?
Oh, right, yeah.
So there's a weight of 5 to this temperature, and there's weight of 1 to this temperature, because it's 50 mil, 10 mil.
Mm-hmm.
And then you divide that by 6,
Okay.
which is addition of those two weights.
Mm-hmm.
But, so no one measured the temperature of this one. However, it is expected that the temperature of HCl would have been would be the same, roughly the same as that of NaOH if both solutions were left in room for many hours or for long enough. Okay, something like that. So these are some of the sources of error. Now let's do some math to do some work on this stuff here. Okay.
Sure.
So I'm gonna do some Excel work. Let me just copy that here. All right. So that's trial 1. That's trial 2. And that's trial 3. Okay. So that's trial 1, 2, 3. Okay. So what I need to do is maybe plot so I have to yeah, it's gonna get a little bit complicated. So let me think about this. So that's an outlier, so I'm just gonna not use that.
Okay.
So let's calculate the change in temperature. Change in temperature.
Mm-hmm.
So that is just that minus that, right? So this is actually meant to be 0 because you haven't added anything. So we're just going to set it at equal to 0.
Mm-hmm. Wait, sorry. How did you do that? How did you just calculate all of the?
Yeah, drag it along. So just write that minus that, and just take this little square there and then drag it along.
Okay, cool.
That means that'll be that minus that, that'll be that minus that, that'll be that minus that, etc.
Okay. All right, cool.
So we're just not going to use that value, and we're going to, because when you don't add anything to the base, the change in temperature must be 0. So I'm just going to set that equal to 0. Okay.
Okay. Yeah.
I don't want to get negative answer. And this is a bit suspicious one, isn't it?
Yes.
So that's pretty similar to that one and pretty similar to that one, right?
Yep.
We expect some similar result for this one, for that one there.
Yep.
Very similar, and these two are similar, right?
Yes.
And these two are similar, so we expect some similar result for this one as well.
Right. Yep.
Yeah.
We state that.
Yeah, you can sort of justify. You can just get rid of them and then justify later.
Okay. Yeah.
So I'm going to get rid of that also. I think there's something wrong with it as well. So what I can do is sort of take the, so make a new table, and then initial temperature, let's just get rid of those two. So let's say average change in temperature, okay? Average change in temperature is equal to 0. This one is average of that, and that, and that, right? So 3.4, and that's average of that, that, and that. So it'll be that plus that divided by 2. So automatically takes care of that. It doesn't divide by 3 because that's an empty cell.
Right.
And that's also average of that and that, okay? So using that, I can form a table with that one there and that one there, and form a scatter plot. So maybe insert. Okay, I need to transpose that maybe. Transpose. That's not good. Maybe just copy that and then copy that and then transpose. Okay. Yeah, okay. Do you follow everything?
Yep.
And I just plot this one just to see the trend, you know? So it's sort of giving me that trend, you know? This is the amount of acid added. This is the temperature change, okay?
Yep.
So maybe I can do that, insert. Yeah. Like that, you know? So change in temperature versus a volume of acid added, okay? Now, the amount of heat generated, okay? So the total, so I can maybe do this one as well, heat generated.
Could you also send me this Excel sheet?
Yeah, I will, yep.
Awesome, thank you so much.
So this is the important bit, okay? So heat generated is actually the mass of water. So the mass of water is that one plus that one. So that's so we're gonna use the Q equals to MC to MCT. Okay.
Mm-hmm.
So that's equal to heat generated is equal to mass, which is going to be 100, which is that one plus that one.
Mm-hmm.
That one plus that one. And then that's in grams. So you got to do 4.18 joules per gram.
Mm-hmm.
That's in sorry, that's total. So just need to do total volume, right? Sorry, just going to be that one. That's the total volume. 4.18 times by that. So 0 heat generated. So this is in joules. And just drag it along. That must be that one there. That must be that one there. That must be that one there. So these are the heat generated in joules according to these temperature changes.
Mm-hmm.
And the number of moles of HCl reacted, okay?
Yeah.
That's really important.
Mm-hmm.
That's 0, of course. Now, if you added 20 mil, you see, all that matters is if you have like 50 mil
Yep.
of base, you add 10 mil, and the amount of energy generated is that. Delta H is the amount of energy generated divided by the number of moles of either that or that. Doesn't matter, right?
Right.
So in this case, because we're adding acid, so I think it's better to base the number of moles on the amount of acid that's added, right?
Okay. Yep.
So we know that from here, number of moles of let's hold on. So 20 mil is added, but the N equals to CV, right?
Mm-hmm.
So concentration is 1 molarity, isn't it?
Yeah.
So the number of moles is simply concentration, which is 1, times by 0.02, which is that one divided by 1,000.
Right.
So 0.02, however, there is something wrong with this one. When you add 60 mil, it's not going to be 60 mil times by the concentration, because when you add 60 mil, like I said before.
Oh, right. There's only 5 moles.
Yeah, only 5 will react with 5, right? So that doesn't count. So we need to be careful. So it must be just 50 mil. So it'll be only that much.
Right.
Okay. And we can plot those two and see if it gives you a straight line. Oh, it does. So this is not a bad result, you know? Almost perfect straight line. So this is heat generated versus number of moles of HCl reacted. And that must be definitely a straight line, right?
Yeah.
If you burn, actually has to be the other way around. The x-axis, the x value must be this, and the y value must be this. Okay.
Oh, right. Yeah.
So, yeah, if you burn 2 mole, then you get 1,000 joules. If you burn 4 mole, it should be about 2,000 joules.
Yeah.
It has to be a straight line. The very fact that this is giving you a straight line means this is a pretty good prep, you know?
Yeah.
Now you can then calculate, of course, you can see that the gradient over here will give you the delta H.
Right.
You know how in the original here we said that it gives you how much? 57 watt. It's about 57.9 kilojoules per mole, right?
Right.
But then we're getting 54,305 joules per mole.
Right.
So that's fairly close, you know?
Mm-hmm.
So that's pretty much what you have to do.
Awesome. That was really helpful. Thank you so much.
From your teacher's, based on your teacher's answer.
Yeah, no, yeah, definitely.
Yeah.
Thank you so much. That definitely cleared because we've never done an electronic prac before.
Yeah.
And I was also really confused by the method. I'm like,
all right, we'll just, so this is due in how many weeks?
In 2 weeks. So.
In 2 weeks. So we have another lesson to do, I guess.
Yeah.
So we'll call it a day here. I'll see you next time.
Awesome.
I'll send you all this stuff, okay?
Awesome. Thank you so much.